Assalamu alaikum, dear students. We continue with our topic of resonance. We have stated what it means. Let me repeat what resonance means just to refresh the idea. Resonance is that phenomenon in which the amplitude of oscillation dramatically increase when we apply a periodic force on a system already undergoing oscillations. So the two frequencies are involved here. One frequency is the frequency of the system that is undergoing simple harmonic oscillation, and the second frequency is that of the periodic force that we have started applying on that system. When these two frequencies match, the amplitude of oscillation increases suddenly, dramatically, and sometimes it increases so much that the system collapses, it breaks down. But often we have some mechanical system in place to prevent that damage, and that is known as the damping. Last time we discussed the frequency response curve, and I would like to discuss it once more. Frequency response curve is something in which we see a curve rising, having a peak, and then it decreases on this side. And I told you we have a frequency on this side and we have amplitude of oscillation along the y-axis. So y direction indicates what is the amplitude of that system, and this is where the frequency, and when we say frequency, it means frequency of both. But at one particular frequency, we see the peak. And this is the frequency which must be the natural frequency of oscillation of the system. And that is why we label it as FR, which means resonant frequency. Since resonance has occurred at this frequency, so this is obviously the natural frequency of that system. So often in the question of this type, after they give you this trace, the next thing they ask you is to identify what is the natural frequency of oscillation of this system. So obviously you read this value from here. There is a certain value here. Let's say it is 250 hertz or 300 hertz, whatever value you read from here. So you read this value, and that is your answer to the resonant frequency. And if this is the resonant frequency, that means this is the frequency of natural frequency. Suppose its value is 300 hertz. Now, you remove that system from that periodic force. You do not apply any periodic force on it, and then you let it oscillate freely. If you let it oscillate freely, what should be its angular frequency? What should be its time period? You can calculate all these things with the help of this 2 pi over omega. So these values could be easily worked out for that system. If the question starts from this graph and they want you to know what is the resonant frequency, and then they ask you to calculate the angular frequency of the system if it is dismantled from the periodic force applied to it, and then what is the time period of it. So all these things can be easily worked out. Sometimes this curve has a slightly different shape, although it has peak at the same position, but the peak is not that high. So what exactly has caused this shape of the graph? If it is the same system, it has the peak at the same position, but it has not that much height. We say that its sharpness has decreased. So sharpness of the frequency response curve, let me write this term here, sharpness of the curve, the sharpness of the curve has decreased now. And the obvious reason for this decreased amplitude, although we have approached the resonant frequency, we have the peak there, there must be a heavy damping in place. That is why the peak could not go to that height. That means this is light damping. This is light damping in place. But this curve must result from heavy damping. So they could ask you a question like this: what is the reason for smaller sharpness of this curve? We can answer by writing that there must be a heavily damped system. One situation is a spring attached to a mass oscillating up and down. You place that mass inside of a medium in which it cannot move easily. For example, a container with the oil in it, when it moves up and down in oil instead of in air, it will rise only to a small height even when the resonance is taking place. So that means you are not allowing that object to move freely. You have placed it inside a medium which is dissipative, which is very dense. So the object has problem moving in this. So it will not have that sharp a curve as compared to the one in which it was moving freely and we observed a large increase in its amplitude. So this is these are some of the points related to the curve, which is known as the frequency response curve when resonance takes place. Now, yesterday we discussed some of the advantages, and we discussed a few of them, and they ask, most of the time they ask 2 or 3 advantages, and I encourage you to go through the book and the internet. There are many more advantages you can find, but at least 3 should be fully understood, so you can write about them. Those 3 that I mentioned included microwave oven, MRI, and the tuning of circuits. Tuning of circuits. These are some of the advantages that we have of resonance, and we make frequent use of them. But there are certain disadvantages. And number 1 disadvantage is that large structures, they start vibrating with large amplitude as a result of the periodic force. So large structures collapse. Large structures collapse. For example, bridges and buildings, bridges, etc. Bridges. One example that is discussed in many physics books is that of the suspension bridge that was first built in America, and it was that large suspension bridge which collapsed as a result of dramatic increase in its amplitude due to periodic hitting of the wind repeatedly, and as a result its amplitude increased to such an extent that it reverted like this and collapsed. Initially they did not understand the reason, but eventually when the research did the research and found many answers to that calamity, they understood that it was the repeated hitting of the wind with the bridge. It had a certain frequency and it matched with the frequency of natural frequency of oscillation of the bridge, and then the bridge started oscillating with a large amplitude, and that is why it collapsed. Similarly, when there are planes passing by residential areas, sometimes window glass shatters. Window glass may shatter. Once again, the reason is that the high frequency of the sound of the plane passing by, and sometimes it's in the region of the high frequency sound, it's a very high pitched sound, and that is the frequency of that sound matches with the natural frequency of vibration of those glasses, and that depends on the size of that glass. Sometimes the large size of the glass is also the reason for this shattering, because if it is small, that requires a very high frequency. If it's a large size window glass, it is smaller frequency at which it shatters. So it's the size, the material of the glass, and the frequency of this, the match. So the frequency matches depending upon the material of the window glass that you have used and its size, the main two factors. So this is another disadvantage, and therefore we either avoid, restrict the motion of those planes through the residential areas. Naturally, we have to restrict their motion through these areas so it doesn't happen. Or if we know the reason exactly which material breaks, which size breaks, we change it to avoid such instances. Then we have another disadvantage is sometimes it is the rattling sound. Rattling sound sometimes is annoying in the vehicles or in anything that is moving on the road, let's say, and it is repeatedly and at a certain frequency it is moving up and down. So there is a certain frequency that is causing this sound. The two frequencies match. Let's say it's a bolt inside the vehicle which is loose and it moves at a certain frequency as the car moves, and if it jumps at a certain frequency, this sound becomes louder and louder as the amplitude of oscillation increases. So sometimes annoying effects that we want to avoid take place simply because some kind of resonance is going on. There are two frequencies matching. So these are some of the examples that we observe in daily life. Obviously, we need to suppress the developing of the large amplitude in all these cases. In the case of large structures, there is a research going on all the time. Now all the buildings that we build in modern and expensive areas, they have those mechanical systems in place which control the large amplitude of vibration. There are springs and shock absorbers connected in the foundation now. Large steel bars are used for this purpose. So they control the uh, amplitude of vibration if it tries to develop. Similarly, in all the cars, in all the motorbikes, we have shock absorbers because we do not want to have very large amplitude of oscillation when we go by them. So some of the techniques that we use uh, in order to suppress the amplitude, in order to control the amplitude, is to introduce the proper shock absorbing systems. Although we don't have those systems discussed in your chapter, but I encourage you to go through some of the detail in the physics books and the internet with all those images, with all those details. So you have better insight of what could be the possible means. Your syllabus doesn't say a lot about this requirement, and they don't ask you exactly how that system works. All they want you to know is that there are means, and at least you should be able to identify some of the ways in which the amplitude of oscillation can be controlled. And it could be a simple means in most cases. With this, we have completed our discussion of resonance and the frequency response curve, its advantages and disadvantages. But before we end today's discussion, let me introduce the last topic of this chapter, and that is ultrasound and how we produce them. Ultrasound is also something that we create with the help of oscillations. And without going into a lot of details, today I will introduce only what is the role of oscillations in the production of ultrasound. And then in the next lecture, we'll understand in greater detail how these oscillations are used for diagnostic purposes. So in order to understand what is the means behind producing these oscillations, we need to understand a few basic things. And the first is piezoelectric effect. This is something we need to understand. A piezoelectric effect is, piezo means pressure, and electric is obvious. So piezoelectric means this is a relationship between pressure and current. So all those crystals in which by increasing pressure we create current by producing the voltage signal at the two ends of that crystal, that effect is known as the piezoelectric effect. This was observed almost 150 years back, and the scientist who discovered it, initially it was named after his scientist, but now it is changed to piezoelectric effect. This is typically observed in quartz crystal. Quartz crystal. Quartz and a few other crystals have a special structures which is tetrahedral structure, and although your syllabus does not require you to explain what tetrahedral structure is and how that structure helps in the creation of piezoelectric, so you just remember that tetrahedral structure of quartz crystal and a few other crystals has that special feature, that special characteristic in which applying a pressure changes the shape temporarily of that crystal, and as a result there are positive and negative charges appearing on the two ends. So if you squeeze a crystal, you place a crystal inside uh, two plates. This is a copper plate, a good conductor. Similarly, a copper plate here, and this is the quartz crystal sandwiched in between. This is connected to the external circuit. So when you create a pressure from the two sides of this plate, we have positive and negative charges appearing on these two plates. As a result, we have a potential difference created between the two plates. These are copper plates. Copper plates. So by creating pressure on the two sides, we create a potential difference, and this is known as the piezoelectric effect. So piezoelectric effect is something in which one form of energy is changed into another form of energy. Therefore, piezoelectric effect, with the help of piezoelectric effect, we are creating a device which is also known as a transducer. A transducer. A transducer is any device like this, which has a crystal in it and which has copper plates at its two ends. It is a device which is converting one form of energy into another form of energy. So when I push it from the two sides, it was the mechanical energy that I'm applying on it, but as a result, I am creating electrical energy. So transducer is a device converting one form of energy to another. So in this case, mechanical energy is converted to electrical energy, and therefore if I apply a voltage to it initially and I vary it quickly, it is possible to create mechanical vibrations in it. So it could be both ways, and that is actually the significance of such a device, that if we apply a voltage signal of certain frequency, let's say I want to create ultrasound, that means I know it should be a frequency above 20,000 hertz. So if I apply a voltage signal close to that frequency, mechanical vibrations will be set up in these plates, and therefore this transducer will be a device which is creating oscillations of such a frequency, and the rest will be the technique about how we send these signals down the body, and how these oscillations go down the body. They get reflected from various internal structures of the body, and we make them take them on the screen and make an image with the help of it. So let me give you an idea of it. So there are three things at least we have understood so far. we have understood that in order to create voltage signal from mechanical signal, piezoelectric effect must be produced. In order to produce piezoelectric effect, we must have a suitable crystal, and it is not possible to produce such kind of effect in just anything. So a proper crystal that we most of the time use is quartz crystal. And when we make this kind of device in which you pressurize to create voltage, or conversely to create mechanical vibrations to give it a voltage, and the last part is something about which I give you a little more detail, and with that we end today's discussion. So the question in the exam, which they very frequently ask, is explain how a transducer produces mechanical vibrations in ultrasound. We have an ultrasound machine, we have a transducer in it, but the question is how it is producing mechanical vibrations in it. The vibrations that we eventually use for the diagnostic purposes. In ultrasound, diagnostic process, you can say. So what you need to understand is that this is the transducer. When you write the answer, you will mention that we have a quartz crystal. This is the quartz crystal sandwiched between two plates which are highly conducting, and these are two copper plates. We apply a voltage signal which is alternating voltage. This is positive side, this is negative, and the next moment this is positive, this is negative. Due to this quick variation, there are vibrations produced. Why these vibrations produced? Because we learned in the beginning that by applying a pressure, voltage is created on this. That means when I have voltage here, there is a stress produced on it. And when I quickly change that direction, during that time the voltage drops to zero, the stress goes to the zero level, but as soon as the voltage changes its direction, it is stressed again, it is compressed again. So repeatedly, when I change this direction going through zero, it relaxes momentarily and then it is compressed. So in this manner, we have mechanical vibrations produced in it. So these mechanical vibrations are vital for all this technique. Without these mechanical vibrations set up in this device, we cannot even think of creating any ultrasound image. So this is the basic question, and therefore this is a very basic requirement to understand how we create ultrasound image. So I quickly make a list of these steps that we have followed so you know exactly how to answer a question like this. So number one, a few points that you must cover in your answer when they ask a question like this is we use a quartz crystal, sandwiched between two plates, between two copper plates. So number one. Number two, these two plates are connected to a circuit through which we provide alternating voltage to this. So through an external circuit, these plates are connected to an alternating voltage. Let's write it here now. An alternating voltage. The frequency of this alternating voltage will decide the mechanical vibrations. So due to this alternating voltage, mechanical vibrations are set up. Mechanical vibrations are set up in the transducer. The frequency of these vibrations, depend on the frequency of the signal that we have provided, and you must have noticed that the mechanical vibration will have frequency 2 times, and let me explain it here. I have to make that figure to explain what I means. I hope you know what 4 points I have covered here. The frequency of these vibrations depend on the frequency of the signal, but exactly how, I go back to that figure, and with that we finish. This is the transducer, and this is the crystal sandwiched inside these two plates. This is positive and this is negative. That means you have a situation like this. So a positive plate is at higher potential now, but when you switch it, this will be at higher potential and this will be at lower potential, but each time there will be a vibration. So as it passes through zero and changes its direction, it undergoes a vibration. That means for one complete oscillation, there will be 2 mechanical vibrations probably. That means the frequency of the mechanical vibrations will be twice as much as the frequency of the vibrations of the alternating signal. So with this, I end here. We'll have more of this discussion. What happens to these mechanical vibrations, how we use them to make images for diagnostic purposes. That will be on the next Monday.